So let's now talk a little bit about the chain rule. And we'll begin by assuming that z is a function of x and y. And let's say that x is a function of t and y is also a function of t. If we then look at the composition, z equal to f of x of t comma y of t, then ultimately z is a function of the single variable t. And so we can ask, what is the derivative of z with respect to t? So to come up with the derivative of z with respect to t, let's let delta z, delta x, and delta y denote the changes that correspond to delta t, which represents a change in t. And with this, we have that dz dt is the limit as delta t approaches 0 of delta z over delta t, and similarly dx dt is the limit as delta t approaches 0 of delta x over delta t, and likewise dy dt is the limit as delta t approaches 0 of delta y over delta t. Now let's recall that delta z can be approximated by the total differential dz, which is defined to be the partial of z with respect to x times delta x plus the partial of z with respect to y times delta y. Now if we take delta z all the way over here on the left and this expression all the way over here on the right and divide through by delta t, we'll have delta z over delta t is approximately equal to the partial of z with respect to x times delta x over delta t plus the partial of z with respect to y times delta y over delta t. And then letting delta t approach 0 suggests the following result. The derivative of z with respect to t is equal to the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. So we can come up with this formula from a tree diagram. We place z at the top, we extend 2 branches from z, and at the bottom of one branch we place x, and at the bottom of the other we place y, because z has a dependency on both x and y. Furthermore, we know that x has a dependency on t, so we extend one branch from x, and we place t at the bottom of it, and we know that y has a dependency on t also, so we extend a branch from y, and we place t at the bottom of it. And then next we label each one of these branches using an appropriate derivative. So z again has a dependency on both x and y. Along this branch we would place the partial of z with respect to x, whereas on this branch the partial of z with respect to y. We're using partial derivatives here because of the fact that z has a dependency on 2 variables. But going down this way, going down this branch from x to t, x has a dependency on only one variable, so we label this branch with dx dt. And likewise over here, y has a dependency on only one variable, so we label this branch with dy dt. To find then the derivative of z with respect to t, we go along this branch and follow down this branch, and then we add to it, going along this branch. In total, we have the partial of z with respect to x times dx dt, plus the partial of z with respect to y times dy dt. So this kind of tree diagram is useful in other situations as well. Suppose that w is a function of x, y, and z. And suppose that x is a function of u and v, y also a function of u and v, and let's suppose that z too is a function of u and v. We can create a tree diagram for this situation. At the top, we place w. From w we extend 3 branches because w has a dependency on 3 variables, namely x, y, and z. And then from x, we extend 2 branches to u and v, since x has a dependency on each of these. Likewise, from y, we extend 2 branches to u and v, since y also has a dependency on u and v, and then same goes for z. And then we label each one of these branches. Along this branch going from w to x, the partial of w with respect to x. Along this branch going from w to y, the partial of w with respect to y. And then along this branch going from w to z, we put the partial of w with respect to z. And then along these branches here, looking at x, it has a dependency on 2 variables, so we need partial derivatives. Along this first branch, it's the partial of x with respect to u. Along this branch, it's labeled with the partial of x with respect to v. Looking at y, again, there's a dependency on 2 variables. So along this branch, we have the partial of y with respect to u. And along this branch, it's the partial of y with respect to v. And then finally, looking at z, along this first branch, it's the partial of z with respect to u. And along this branch, it's the partial of z with respect to v. If we're interested then in the partial of w with respect to u, indeed because w depends on x, y, and z, and since each of x, y, and z depend on u and v, ultimately w is dependent on u. If we want to find the partial of w with respect to u, what we need to do is follow each one of these branches down until we get to u. Beginning with this first branch, we have to go this way to get to u. We have to go along this branch, followed by this one. And then, going along this way, we have to go this branch, followed by that branch. And then finally, going this way, we need to follow this branch, followed by this one. Putting it all together, we have the partial of w with respect to x times the partial of x with respect to u, plus, going this route, the partial of w with respect to y times the partial of y with respect to u, plus finally going this route, we have the partial of w with respect to z times the partial of z with respect to u. And that's how we define, in this case, the partial of w with respect to u.